All right, let's have a closer look at piecewise functions. The things we need to check for are gaps and sharp corners to find parts of the function that are not going to be differentiable. So this piecewise function has two conditions. F of x is equal to x for small values of x. So if I'm going to graph this, as soon as x is less than 0 or equal to it, it's the line y equals x, which is just a 45-degree angle straight line there. And I can see that it includes when x is equal to 0. So I can use a closed circle to show that the origin is part of that line. Open circle would show it comes up to but doesn't include that point. But as soon as x is greater than or greater than 0, it follows this rule. It's basically the curve y equals x minus x squared. Now, if I was to factorise that, I can see that I'm going to get this. And if I want to know how to graph it, let y equal 0 to find the x-intercepts. Either x is 0 or x is 1. So it goes through the origin and the point 1. And I can see that it's an upside-down parabola because I've got this negative value of x squared. So I can basically draw this in like this and say it's something like that. Now, checking for gaps, well, I can draw the whole thing without lifting my pencil off or my pen. So I know that we're fine, there's no gaps there. But I've got to now check for sharp corners where there's the join. Now the join happens when x equals 0. So it looks like it doesn't seem to be a very sharp corner, but you can't rely on your drawing. After all, it could have gone more up like this. Who knows if the scale of my drawing is correct. And if this was a sharp corner, it would be undifferentiable at x equals 0. So the way that I check it is I differentiate it to find the gradient. And differentiating this part, I get 1. Differentiating this part, I get 1 minus 2x. So I have a little rule there for the gradient of both parts of the curve. Now if I find what the gradient is actually at 0, according to both rules, the top one is 1, so it's always going to be 1. But if I sub x equals 0 in here, I've got 1 minus 0, which is also 1. And they are the same. That means just this side of the origin, we have a gradient of 1, and just that side of the origin, or pretty much on the origin, we also have a gradient of 1, which means there's no sharp corners. So this is differentiable at all values of x. If I look at an example more like this one, I've got to check for gaps and sharp corners. A great strategy is to draw it. So drawing this one, I have x squared minus 1. Y equals x squared is a parabola, and if I drop it down 1, it will look like a parabola that's just been shifted down 1. That's for all the negative values of negative values of x. So it'd be something like this. And it's been dropped down 1, so it's going through -1, and it includes that point, 0, -1. This other part of the domain, when x is greater than 0, this is a parabola that's been lifted up by 1. So it's going to go through this point, but not include it, so I'm going to use an open circle to show that's not part of the graph. I need arrows on the end to show that things go on forever. And here I've got a graph now of this piecewise function. Now I can clearly see there's a gap. So straight away I know I can't differentiate this at x equals 0. So if you were asked about it, you would just say it's not differentiable at x equals 0. And once you've found that it's not differentiable for one of these reasons, it's almost a little bit of a waste of time looking for sharp corners. We already know that there's a good reason we can't differentiate it here. And yet it's smooth and continuous for the rest of the domain, so there's no reason to go and check for the sharp corners. If I did need to, I'd do it with this method. Find the gradient for both parts, the gradient function, and then sub in the area that you're interested in looking for a sharp corner at.